we wanted to have a panel on crypto because we're all users of crypto. Many of us implement crypto. Most of us aren't cryptographers. And so we've asked 3 cryptographers to come and just talk among themselves or answer any questions that any of us in the audience might have about what's going on in the world of crypto, what should we be aware of, what should we be afraid of, what should we be depressed about, and what can we possibly do to fix this.
We don't have enough time if we're going to talk about what we should be depressed about.
Fair enough. So let me introduce to you Dan Bernstein, Matt Blaze, Tanja Lange, and let them each say a little bit about something that is of interest to them, and then we'll open it up for questions from all of you. All right?
All righty, we decided to go in alphabetical order, so that gives me the luxury of giving you some warnings. First of all, there's one that's up on the screen. It's very difficult to discuss today's cryptographic software without using the word, I can't read the bottom there. Oh, thank you for the beep. We also, so anybody who has trouble with this, sorry, we're going to have a frank discussion here, so if you have trouble with this, please leave the room. Some other thing I'm supposed to warn you about is that we have some completely unnecessary naked pictures. Here they are. So the title of the panel was something like The Future of Crypto From Here to Guarantees. Now, I'd like to take the attacker's perspective for a moment here. The current situation where we are right now is that occasionally crypto is actually creating an obstacle to the attacker. And that's a problem. What we want is a guarantee that crypto is never getting in the way. So what do we have to do to get from the current crypto almost always failing to a guarantee that it really always fails? Well, there's several things that we can... Why is everybody laughing? There's several things that we can do to improve the situation, to move towards guarantees that crypto is just never protecting the user. First of all, human resources. I mean, obviously, we can just pay people to do what we want. I mean, hire the people or pay them to do something which is screwing over the user. But, I mean, that's kind of obvious and not very subtle. Maybe more subtle is the following. We can take people who are potential future human resources, the students, kids who are interested in crypto. I mean, crypto is cool. It's fun, you know, spy versus spy. And then there's tons and tons of people who get interested in it. They'll read these fun books and articles and hear about NSA and so on. And then, well, maybe they don't come work for NSA, but maybe they want to go into, like, public sphere of helping people do crypto. And it would be nice to deter them. For instance, someone who goes to graduate school and does cryptography, well, they want to do cryptography. And they go to grad school, they get through whatever reasonable courses, and then finally they find someone who's identified as an academic cryptographer to lead them on a career in cryptography, to introduce them to research problems so they can help the user. And what they end up working on is something like, say, indistinguishability obfuscation, or fully homomorphic encryption, or leakage resilience. And I'd be happy to elaborate on these in more detail. If any students might be in the audience and interested in the importance of these areas, then I can help you get away from real cryptography and explain to you what these things will do. And that's what actually most people doing cryptography end up doing, is things which are not actually helping the cryptographic user. I don't mean to say that every advanced cryptographic functionality is something which will never be implemented, but there's no current risk of any of these things being implemented. Obviously, if we're having trouble just encrypting data to ourselves or encrypting data between two parties, then something fancy, some encryption with lots of adjectives on it, that's not going to work either. So the only real risk that we're facing, the guarantee that we're missing as the attacker right now, is that cryptography really is going to fail in the simplest cases. The fancier kinds of cryptography, those are obviously failing anyway. So, okay, suppose somebody gets past all these distractions and they get into actually working on crypto that might actually do something for the user. Then, well, another thing we can try to do to distract them is to tell them, hey, focus on attacks. Now, this is something which is culturally really, really nice. I mean, everybody, you know, you put up an attack and you get applause, like, wow, you actually demonstrated a working attack, and then you try to measure the attacks, you try to say, hey, can you make the attack faster? I mean, you manage to do that attack, you manage to break the user's security in an hour of CPU time. That's a long time. Can you get it down to half an hour, a minute? That would be a better attack, right? And so lots and lots of people spend lots and lots of time optimizing attacks. I do quite a bit of this myself, and it's not actually something which makes a difference in security. It generates lots of papers, it keeps cryptographers employed, but it doesn't produce any more secure system. So, okay, that's also pretty good to distract people from working on cryptography. And then finally, if someone actually gets into working on something that is recognizably producing better cryptography, that is creating a risk of helping actual users protect themselves, then let's try to make that as complicated as possible so that it's not going to be secure. And then we can get a real guarantee that something's going to go wrong and it's going to fail. So obviously there's all the stuff surrounding cryptography. I mean, the rest of computer security is in not such a pretty state either, so we can maybe guarantee that cryptography fails by putting it on devices that we can break into in lots of other ways. But even if that doesn't happen, even if it's the cryptography itself that we have to make fail, it's important for that system to be something really complicated. For instance, algorithm agility. If you can't get one cryptographic system working right, and you end up with some sort of weak cryptographic system, how about put on another cryptographic system next to it and have some more knobs and adjustments, and let's make it as complicated as possible with 35 different layers of options for tweaking your cryptography, so nobody at any point between the implementer and the user has any idea what any of this is doing, but there's all these knobs to play with, most of which are insecure. Somebody's going to get things wrong. If you can make the system complicated enough, it will fail. And okay, if we can put more and more effort into making all of these aspects of cryptography fail, then maybe we can actually reach a guarantee that the user will have no protection. Thank you.
Okay. So I'm not quite sure why Dan is concerned about having guarantees that the crypto will fail, because I'm not sure why that's ever necessary or helpful to require the crypto to fail. From an attacker's point of view, I want to think about, maybe the only example I can think of an actual giant government conspiracy. And the actual giant government conspiracy that I can think of is the decade of the 1990s, in which the government managed to brainwash the entire computer security community into thinking that the important thing to spend its time on was fighting over export controls for the right to use and export PGP, instead of spending our time making software that secures things usable. Right, so all of this great talent, and in particular, that all of the people who actually understood the human interface and the uses of computing well enough to be able to spend time lobbying about policy and thinking deep thoughts about how public policy should respond to cryptography, instead of actually making usable, secure systems, we spent it all arguing with the government. And by 1999, we won. But it didn't matter because we were all exhausted at the end of that decade, right? We were too tired to actually build anything by the turn of the century. So we kind of ignored, we spent all this time fighting for the right to use PGP when we really should have been spending that time wondering why anybody would ever want to use something like PGP, because it's actually too hard to use. We forgot how to engineer usable crypto systems, and we forgot that that was a problem because we pretended that our adversary was export controls. Now, I'm as guilty as anybody about over this. I pretty much wasted the 1990s on this as well, and I'm glad that we won. But I also regret the opportunity cost of fighting that battle. I look at what should be the simplest problem in the world, and you can take 1990 crypto and maybe tweak the parameters a little bit to account for Moore's law and use things like triple des instead of des. But you can take all the cryptographic primitives that we had 20 years ago and build a system where the crypto isn't going to be the thing that fails, because most of the time you're going to be sending clear text. And we need, this is the problem. All of the people that, that people like Dan are encouraging to spend their time doing a PhD in crypto are people who are not only are they not doing useful things like curing cancer, they're not even doing useful things like trying to make crypto usable. So I think that, the best thing that we could do to get to guarantees of security is fire everybody on this stage.
All right. Should I leave?
Yeah.
Well, that puts me in a difficult position. Maybe I should leave now. So we were organizing things by alphabet, but also I was saying, well, I might have a slightly more positive view on things.
That won't be hard.
Slightly more positive. But before I say that, I would say that Dan was leaving out one thing that is usually also wonderful in the way of getting secure crypto deployed, namely standards. So if you actually have something which would run well, which would be secure, in Dan's mind, if somebody accidentally did something secure, the usual weapon is to say, oh, but it's not standard compliant or it's not certification compliant. So that's when you have the last possibility of saying, no, stop the good stuff. Now putting my own head on, I would say that in crypto we actually have a chance of doing something good. Yes, it's largely crypto from the 90s, but we have learned some more things. We can do better things. We could do things with the 90s crypto, and in some senses it's good because, well, whatever patents it was based on have expired by now. But sometimes, and luckily lots of times, good stuff is not patented or the patents have expired. So we can actually do cryptography in a secure way and then bring it to usability by having it implemented. So one positive example where I hope that Matt won't say that the students we put on this were wasted was a crypto library by Dan, a former student, Peter Schwab, who's now professor himself, and myself, called the Salt Library, well, NaCl, so chemical symbols for salt. So the Na is the networking end, and then there's a cryptography library. The networking part is kind of there is a little bit on that because we had an EU project paying us for doing it, but what we really liked doing was the crypto part, and we wanted to have a library which doesn't have all kinds of knobs, which was just doing one thing and was doing it right. And so we're offering the user a kind of one-call crypto, it's called Crypto Box, which does for you, if you have seen a person, so you have the person's public key, it then does a Diffie-Hellman key exchange, so it's a one-time, it gives you forward secrecy and all that stuff, and it does a ephemeral Diffie-Hellman key exchange, derives a symmetric key from it, makes symmetric encryption with an authenticator. You can have arbitrarily long messages with this, but this is all hitting from the user. The user calls CryptoBox on the message, and then the library does all the stuff about wire format and such things. It's a one-push encryption, it's a one-push decryption, so there's the CryptoBox, which, well, secures things, puts it in a box, put a lock on it, ships it over, and then there's the box open, which opens the box. Two simple commands. We do allow users to dig deeper into the library, but the cryptographic user or the security user who doesn't want to take a course in crypto and get distracted by fully homomorphic encryption and stuff, he or she can simply take this library and have a one-push encryption option. There's also a signature option in it, and we think that with that we have done the better than 90s crypto, better in the sense of more efficient and more secure implemented. Because in the 90s, at least outside the government, we didn't know so much about side channel attacks. There were some people noticing that things take different times, but they didn't think about it as an attack mind. Now we know that if you see a timing difference, which can be traced back to either the key or the message, that can be used as an attack. So there has been an attitude change since the 90s towards now that our implementations have gone better, or we are more aware of attacks, where the research community knows it's important, and hopefully the implementation community is doing this. Our library has been designed with this in mind, so all the functions in there take constant time independent of what the key is, take constant time independent of the messages. Of course, if you have a message that's longer, you get the message length, but that you also see from just observing the traffic. So if you have an application where even the length of the message has to be secret, then you have to use message padding and just, well, always fill it up to whatever your message length maximum would be, a few kilobytes or something like that. So I think we have done something between now and the 90s which has gotten better. Nothing of this is new, brand new research. I would say the last things coming in there have been done in 2007 from our library. There's a signature from 2011, but all of that is based on prior research. But on the, I just disagree that there's nothing happened since the 90s. And I disagree with Dan, but that was the whole point of the setup, that crypto can't help you. So I'm the person here to say, yes, crypto can help you, but we would like to help in a way that is nicely boxed and not confusing with lots of options. Thank you.
So now is our time, because you've been waiting for this all your lives. This is Ask a Cryptographer. So please, discuss questions, any ideas, any topic you would like to be discussed, given our certain disclaimers. Please.
I'm Jeffrey Goldberg from Agile Bits, and I'd like to just follow up on these. In a sense, two of you talked about usability. One is usability for the user, and the other is usability for the developer, giving something a software developer can use, and right? But when it comes to usability, I mean, that I think is probably where the research should be. And to follow from Matt's example from a couple years ago, things like the distinction between a password for authentication and a password for encryption is a subtle concept. And if users need to understand that distinction to not shoot themselves in the foot, it's not just building nice user interfaces to things. These are actually difficult problems because if people don't understand concepts, they will shoot themselves in the foot. I spent a good chunk of the 90s trying to teach people PGP. I failed. If people have to understand the distinction between trusting someone's identity and trusting them as an introducer, it's not going to work no matter what user interface you put on it. So I'd just like to talk about how do we make progress on these hard conceptual things.
Maybe we can replace all these complicated web of trust concepts with making an unauthenticated connection to an untrusted key server. Would that improve the situation?
Yes, actually. I mean, I think there have been all sorts of successes in the deployment of crypto where you don't have to actually understand anything about it being used. Like, so, the mobile telephone network in the United States is horribly vulnerable to interception, but over-the-air interception of phone calls by, non-state actors has ceased to exist as a problem, right? I mean, virtually, asymptotically 100% of cell phone calls are encrypted over the air, and it's no longer possible to get a cheap radio receiver and listen to your neighbor's cell phone calls. That's been a huge victory for crypto because it's completely invisible, right? And it's not doing anything particularly novel. Now, there are many things to complain about other security aspects of mobile phone calls, but one serious existing problem completely went away as a result of it. Yet, while that was happening, in spite of the fact that I actually do know the subtle differences between authentication and identification and confidentiality and signature, I still don't know how to send Dan an encrypted email message.
Yeah, I mean, at the beginning you were saying you want to make a difference between the crypto implementer or the library user and the user. So I would never recommend the Salt library for any user, but I hope that for somebody who needs the crypto as a plugin, this is helping. I'm certainly not the right person to do user interfaces or whatsoever, so don't ask me for that, and I know that I'm incompetent there. So if I think something is obviously and easy, then just ask my students and they will say, no, it's not. So, but yeah, so helping the crypto implementer or the security implementer get some good crypto, that's something I think we can do. Then helping that to be usable, I think needs a wider area of study. I'm not sure that a trained computer scientist is the right person to answer this. I think it needs something, needs experiment, it needs people to volunteer, and we need a broader spectrum of like our students to test it out because, well, our students are kind of influenced in thinking by what we teach them.
Maybe to add, I'll take off my attacker hat for a moment here. To add a positive comment about something that I think is a very interesting direction for managing user identities, cryptographically secure user identities. There's something called the GNU-net Alternative Domain System from Christian Grothoff and collaborators. And that one has a very usable way to manage the identities of the keys that you're talking to. And it's a step forward from Spooky, for example. It's something where I haven't before seen a usable way to keep track of secure public keys. And this, I think it crosses the usability boundary. Whether it's at the same time achieving the security that you want is a different question, but it's a very interesting system, something to take a look at.
Since dense attack hat is free, this problem of key exchange can easily be used by government-issued keys. And whom do you trust?
So that leads into a question that I'd like to ask you. You know, given the recent revelations of flaws and the allegations of tampering with cryptographic standards, what do we as a community have that we can actually rely on? Dead silence.
Nothing.
Nothing.
Yeah.
Sorry. But you're
So,
supposed to have all the answers.
Actually, the elephant in the room problem is that, there's one person on the planet who knows how to write secure software, right? It's Dan. And, he hasn't been able to explain how to do it to anyone else, right? And, fundamentally, we've got crypto, which is generally pretty good as far as we can tell, that in an unusable package that's made out of chewing gum and baling wire, right? Mm-hmm. So the crypto is the good news in that.
Wow, okay. Let me say a little bit in favor of simplicity, that I think there's a huge gap between what we're accustomed to seeing for cryptographic software and what can actually be done. If you look at how much code there has to be, you look at something like OpenSSL and it's this monstrosity, and people are, trying to fleanse it a bit and trying to rewrite it in a more comprehensible internal way, but preserving at least the the developer interface to it, preserving a lot of the internal structure. It's going to remain a mess with all of the attempts to improve and clone OpenSSL. And the same is true for lots of other cryptographic libraries out there, that they have tons and tons and tons of code. Now, where does this code actually come from? Let me give you just one of many examples. If you look at the list of elliptic curves that are in OpenSSL, I won't try to fire it up on the laptop here, but if you say something like OpenSSL ECParam list, I forget the exact options, then what you get is a list of something like 50 different elliptic curves that OpenSSL knows about, where there's different code paths for those different elliptic curves. And if you dig a little more into the list, there's one elliptic curve, which is one that a lot of people know about, the NIST P224 elliptic curve, one of the standard elliptic curves widely deployed, almost as popular as NIST P256. And then somewhere down the list, there's some ANSI WAP something blah, blah, blah curve that nobody's ever heard of, which turns out to be exactly the same curve, but it's a separate chunk of code. If you ran a deduplicator on the list of curves, you wouldn't catch it because there's some metadata which doesn't match. There's not just the name, but there's something else, the seed, that doesn't match. And it's just another piece of code. The implementation is done differently. If you change the name, it should be interoperable, but it's a whole different code path. This is some internal silliness where you can find thousands and thousands and thousands of examples of this throughout our cryptographic software. And this is actually encouraged by how people are trained to design cryptographic software.
It's interoperable. I mean, if I'm using one of them, you use the other, we can talk to one another. You wouldn't even notice it from that.
Yeah, but there's still two different code
Oh,
paths.
yeah, and one has been looked at, the other one hasn't.
Yeah, one of them's constant time, one of them's not. It's just amazing how messy this is, and it's completely unnecessary. Even things that people will often argue for, like, oh yeah, it's really important that we have a choice between weak algorithm A and weak algorithm B and weak algorithm C and weak algorithm D, so that in case weak algorithm A is broken, we can pretend that everything's fine by switching to weak algorithm B. This sort of thing can be replaced by just implement strong algorithm Z and be done with it. And then that's not going to fail. Of course, there have been cryptographic failures, things like RC4, things like MD5 was used to break into some Iranian computers with Stuxnet, or was it Flame? I'm sorry, confusing my botnets possibly. Was it Flame? Okay, thanks. So Flame was breaking in using some combination of Microsoft terminal server doing code updates with MD5, and well, it was using an actual cryptographic attack on MD5. Now, you can point to examples of these cryptographic failures, but they're in algorithms that are almost pre-1990s. MD5 was like 1991, and RC4 was late 80s. These are algorithms which should have been replaced long, long ago. And if you switch to new generation of cryptography, you just don't get these failures. So pick a cryptographic algorithm. Don't pick something that's 30 years old, and then implement that, implement it in the simplest way, and you get a much, much smaller code base than what we have now. Don't put in random ping options into your protocol. Don't put in options that you don't need. Crypto doesn't have to be that complicated. As a concrete example of how simple it can be, the salt library that Tanja mentioned, there's a tweet version of it called TweetSalt, where you go to twitter.com/tweetnacl, and you find 100 tweets, which is a crypto library.
The same crypto library that we have with highly optimized assembly code as salt, TweetSalt has the same interface. You can replace one by the other. You don't get the same speed, but it's 100 tweets or one A4 sheet, letter-sized sheet.
We have a question.
Yeah, I'm David LeBlanc from Microsoft. And it's part of my job to try and make sure that when people decide to use cryptography somewhere in Windows, that they put the building blocks together in the right order. And I think that that is an area which is lacking in work. And there's been one recent paper that I saw that I thought was very helpful, where they looked at the whole Mac then encrypt or encrypt then Mac problem, and they came up with 160 different ways to assemble the building blocks and decided that 9 of them were reasonably secure. And I think that if we did more of that sort of thing so that we came up with higher level structures, because that's what people really need is a higher level structure, then I think that that would be a productive step.
Mm-hmm. I think there hasn't been so much research because it's been like already in the Schneier and Schneier-Ferguson books, like one should not do the Mac before the encryption, so it's something that everybody has been preaching since years. So for the research community, it feels like it's a solved problem. And,
right, but there's 160 ways to do encrypt then Mac.
Exactly.
And 9 of them work.
Mm-hmm. It's just a question, do you want to identify all the ways that it doesn't work, or you want to find a good way that works and stick to it?
Exactly.
And we are usually we find a good way, prove it's good, and then we're done. We don't need to look at all the other ways that possibly can work and most likely don't.
But I think we're lacking in having found the good ways to assemble things. They're certainly not, I think, well documented in reasonable ways. I mean, we find so many different ways that things go wrong. It's amazing. You know.
One of the things that I like seeing happen in the cryptographic community is that there's efforts to have people come together and build solutions that are slowly getting towards what the user needs. I mean, what the user needs is typically something like a secure session, or, I mean, you know, something which is comprehensible, like, what am I getting out of this? I want to talk to this server. It can get more complicated than that. But, okay, crypto is slowly moving towards, for instance, look at the AES competition from the late 90s and into about 2000. Now, that was looking at a block cipher. So it's saying we have a cipher, it takes like 16 bytes and encrypts them under a key to produce 16 bytes. And then you have to do all sorts of complicated stuff to safely encrypt a longer message. Now, you can do that, but then you also have to authenticate, and well, okay, so there's all these extra problems. Then after the AES competition, there was a similarly focused effort called eStream that was well, centered in Europe. There were some Americans involved as well, and Asians, but this was the eCrypt Stream Cipher project. And that one was saying, okay, we actually need to generate a lot of random data to encrypt a long message. And now how do we do that? And they also said, you know, you can also do authentication. Not many people went for it. It was maybe stepping a bit too far for the cryptographic community. And what really gives us confidence in these cryptographic algorithms is if you have 50, 100 people really bashing on the algorithms for years and saying, yeah, we're confident in these. We've studied these. And we know these are secure. And that's what happened for AES. Some implementation problems for AES, to a timing attack disaster, but as a cryptanalyst, if you're saying, is the AES output going to reveal anything about the key? The answer is no. It is very, very safe from that perspective. Same thing for eStream. Lots of people. There were about 50 people who submitted to AES. There were 100 people who submitted to eStream. And by the end of it, there were some stream ciphers that people were really confident in. And now, well, there was the next competition was the SHA-3 competition, saying, okay, we need a similar confidence in our hash functions. And now there's a competition for the new Caesar cipher. So Caesar is the competition for authenticated encryption, security, applicability, and robustness. So that's going for authenticating and encrypting a long message. That's still, you know, it's like one packet. I mean, we're still several steps away from a secure session, but you can imagine that if this keeps going for another 10 years, then it'll actually be at the point where the cryptographic community can say, okay, time to have a competition for a secure session, and this will provide at least what quite a few users need, and we're confident enough about the building blocks, and then we're going to be confident about how to do the secure session, and then here's the solution, and stop having to worry about it.
I mean, the competition would find even better solutions than we currently think of.
Yeah.
I think cobbling some stuff together, what we did with Salt Library, I expect to be just fine in 10 years. I don't expect anything to be wrong about it. However, I can imagine that research finds something which is better, in particular if you put 100 or 200 people focus their attention on the same problem. And also the competition has this nice effect that you have smart minds submitting, and then the same smart minds who want to win try to beat each other's ciphers. So there's a lot of competition, there's lots of interaction. There's actually, so for the CSER competition, it's just started earlier. It's now in its first year. There's a conference the next 2 days up in Santa Barbara. And now we see that, yes, people are beating competing ciphers, and we're getting really good cryptographers and cryptanalysts to look at other ciphers, which if they were just published at some random conference, we wouldn't actually see.
But maybe I don't really need a new cipher like Matt said. Maybe AES is good enough for quite some time to come, and SHA-512 is not too shabby. And
you want AES in counter mode?
And so on. Well, you know, different modes, okay, I grant you that. But if you just worked from the assumption that, okay, so we've got a good hash, we've got a good encryption algorithm, now how do I put the pieces together correctly?
Yeah, that's what a lot of the submissions to CSER are doing, is taking established components like AES and then fighting about how to put them together correctly. Mm-hmm. And even that, like you were saying, there's a lot of ways to screw it up.
But I like the idea of a crypto implementation competition.
Yeah, but I mean, it would be. I mean, Dan would just win.
Yeah. I'm okay with that.
All right, cut it out already.
Yeah. Please.
You started off speaking about that you thought homomorphic encryption and these kind of fancier or flashier areas were not very useful or distractions. I was hoping you could talk a little bit more about that, whether you thought they were chasing toy problems or whether they were built on shaky foundations or there's just more pressing things. If you could go into a little more detail about that.
I get worried that if I start ranting about this, we'll be completely out of time, but...
We've got time.
And out of words.
Oh, yes, that's right. There's the code of conduct. Okay, let me give you an example, leakage resilience. So this is maybe a simpler example to tackle than indistinguishability obfuscation. Leakage resilience comes from the following. There's lots and lots and lots of ways to leak your keys through side channels. And there have been some great talks about that here, and there were also a couple interesting talks up at Crypto earlier in the week. One of the ways that you can deal with these side channels is say, okay, we're going to have some absolute rules, like you have no use of any instructions which are going to leak any of your secret data to the branch predictor or to the cache or anything else that's going to take variable time, or possibly, conceivably, take variable time. Now, you can follow those rules, but then the attacker starts getting closer and starts seeing acoustic emanations from capacitors inside your computer, or starts seeing maybe some electromagnetic emanations, or something else, some side channel where if the attacker is far away through the internet, they'll never see that. But if they're close to a smart card or your laptop, well, there was a great demo at Crypto during the rump session of key extraction from a laptop. First of all, clipping something onto, okay, if you're, the way they explained it was if you're an electrical engineer and you have some electromagnetic emanations, you're trying to get rid of them, you ground things. But that doesn't make them disappear, it just spreads it through the ground. So okay, they first tried clipping something onto the case of the laptop, and through that we're extracting a secret key. And then they said, well, you don't really need the metal touching the laptop. So then they were doing like human touching the laptop, and then they replaced the human by a sausage touching the laptop. It was a fantastic demo. It was video online. And well, okay, if you're trying to protect against these attacks, then the starting point is do constant time, but then you have to do so much more to protect yourself against really nearby side channel attacks, because there's so many ways to leak physical data through physical channels. So what do? Well, you try to shield yourself as much as you can. You try to mask your data and prevent it physically from getting out. Try to put in Faraday cages and stuff. And you try to randomize things and do things like secret sharing, split your data between example from this morning was splitting your data between one virtual machine and another. And if you combine a lot of these techniques, then you can actually resist a fairly determined side channel attacker. It starts getting expensive. So, okay, what's the best trade-offs? If you have some cost limit on how much you can do to protect against side channels, how much does it cost you? How much does it cost the attacker? There's some curve there that people have been trying to work out for many years. And that's one of the main focus areas of the cryptographic hardware and embedded systems workshops that happen every year. Now, into this picture comes leakage resilience. And the advertising for leakage resilience says, instead of trying to understand physics, electromagnetic radiations, sausages, you try to say, let's just do something mathematical which will protect against any side channel. Now, that would be really, really cool. If you could just do something like at the software level, use the following algorithm to compute your cryptographic function, and that is going to protect you against any side channel. So we don't have to learn anything about the physics and the sausages.
We can even prove something.
Yeah, well, oh yeah, proofs are good. Proofs give you papers. Now, the problem with this is that it's impossible. You can't actually have this magic mathematical protection against all the physical side channels.
Wait a second, I couldn't define a model.
So you set up definitions, and the definitions will say something like, okay, we're going to allow the attacker to see any sort of side channel, any sort of leakage. They'll be peeking at your screen, they'll be peeking at your keyboard, peeking at your CPU, but they will only get 1 bit of data every second.
And how do they know that?
The question was, how do they know that? Yeah.
Because it's in the model.
It's a definition. You don't have to prove anything once you have a definition. And then once you have that definition and you start...
Don't dare to attack outside the model. We don't like that.
That's cheating.
Then you can start proving some theorems. And this is a field of research called leakage resilience, which says you have a certain amount of leakage that happens. We don't know anything about the leakage because the whole point is to not know anything about the physics of what's being leaked. And then you can prove some theorems saying if there's not much leakage, then the following cryptographic system is going to be secure. As you can tell, I don't have a whole lot of respect for this field, but if you're thinking from the attacker's perspective, it's a great way to distract people. I mean, look, you can publish these papers at top conferences. Crypto had several papers labeled as side channel papers. One of them was actually looking at side channels, and the rest were looking at leakage resilience and similar concepts, which I don't see any practical applicability of. I could keep going similarly into indistinguishability obfuscation, but I really should stop now. It's good for my blood pressure.
I want to, people say I'm a cryptographer, but that's just a nasty accusation they make. I want to defend impractical work because we don't actually know when it will be practical or what it will tell us. I mean, being able to bound something by you only get 1 bit every second or something like that obviously doesn't have direct applicability into a system that we're actually building. But it's not, that's not the same as saying that thinking about that doesn't have benefits, right? And, thinking about, well, here's the model that we can prove something about. Notice how far away that model is from my actual computer. And, that's valuable by itself. So I don't want to, I think it would be a mistake to take away from your comments that fundamental and theoretical work in security is of no value. But I think it is fair to say fundamental work is not of immediate practical value. And the truth probably lies somewhere between those two extremes.
It's a little worse than that because, I mean, historically where leakage resilience came from as a research area was actually the chess community trying to formalize the physical effects that we are seeing. And in Europe we had this EU project that I mentioned, and we had endless battles about how one could formalize leakage or side channel attacks. For instance, saying, okay, what do you see when you're taking oscilloscope measurement? Does it depend on the Hamming weight of the bits that you're seeing going by, or is it depend on the last bits or the top bits or some other complicated measure? And we had endless fights about this. We couldn't actually finish the report in time because the different factions couldn't decide on what is the right model. It's that complicated. And then finally there was a paper by Moti Young and François Xavier, which got a really hard time getting into a conference where they were starting a small step towards formalizing the actual physical effects and saying, okay, well, once we have done this, we can maybe build something on top of it. And based on that paper, from the very other end sprung this leakage resilience story, starting with models which are very, very unrealistic and hasn't actually evolved to anything close to realistic. To say how unrealistic it is, it's actually often making attacks easier because the easiest defense is, well, you want to have 80 bits of unguessable keys, you will leak 1 bit per second. Hey, how about I make my key longer? Then you will have fewer bits that you know, so there will be 80 unknown bits left over. Now, if I'm actually sitting there with an oscilloscope and have a pin on the chip or have a radio receiver next by, then I will actually see the long key and I'll get long data from it. So I haven't actually made anything more secure. And when you look into the how involved those proofs get, then it often gives me more information than I would otherwise have had about the system. So I think at the moment it's going in the wrong direction.
I think for me what matters about the question of how you're analyzing something is not whether it's labeled as being fundamental or labeled as a model or labeled as definitions and so on, but are you setting up the right incentives so that people are going to move towards something that's actually secure for the user? And if you say your incentives are, we want to publish papers with proofs and we don't want to understand the physics of what's being leaked, I think that's unhealthy. One of the reasons that I've got more respect for the USENIX Security Symposium than I do for, say, the crypto conference is that I think here people are actually caring about the real world security. And I think if you set up a structure where people are encouraged to ignore the physical effects, then that's just going too far towards theory, and it's not going to be useful. So with all due respect to, say, theory and foundations, I think it's good to have clear definitions and be able to understand what's going on, and if you can abstract away from details, that's great. But if security requires you to look at the details, you have no choice but to dig in and actually see what's going on.
Brian.
Hi, Brian Warner. I had a question about knowledge transfer and education kind of to the industry. I'm a software developer. I do design cryptographic things to put the building blocks together in the right order for things that are very mundane from the point of view of the academic community. And I find it challenging to develop confidence that I'm putting the blocks together in the right order. And you try and deal with this by publishing everything, having everything open source, talking to as many people as possible and get reviews on it. But I find it really challenging. And it feels like a lot of the information coming out of the academic community is moving very, very slowly into industry. Trying to use the NaCl library as opposed to something older, something AES, it's kind of an uphill battle to use something that is less than 20 years old. And I wonder if you have any thoughts on how to get the information here and the common knowledge, things that everybody, the baseline of what modern cryptography would use here. How do you move that out into the rest of the field where these people are not reading these papers all of the time, they're not up to date with it?
Yeah, I mean, it's funny that, a couple years ago, my answer to that question would be, well, you shouldn't be doing any of that stuff. You should be using a well-trusted standard library like OpenSSL. Right?
Or implement the standards,
Yeah.
get certified.
Right. Yeah, I hear NIST has some good crypto standards.
And actually, a lot of the pushback I get is somebody saying, well, but we have this FIP certified library. If we use that, we'll be safe, right?
Yeah.
Why are you even considering using something other than that?
Right. And, for the benefit of anybody who wasn't noticing, our laughter about this was sarcasm, right? That we wouldn't give that advice today. So it's, unfortunately, use something that be in the same boat as many other people as you can find is kind of good advice, even in spite of the fact that we've seen some catastrophic counterexamples recently. It's unfortunately, I'm not going to say OpenSSL is the example anymore. And there's a certain NIST elliptic curve standard that I'm a little less happy about than I used to be. But the advice about being in a really large boat with other people, it still stands.
So to partially answer your question and come back to what Sally was asking at the beginning, like how can we get somewhere, how can we make things better? I think we're in a somewhat better position than, say, a year and a half ago, in that people don't blindly follow the advice that Matt was currently saying, that we have at the moment reached a state where people are a little more open towards changes. They are more concerned about, well, where did these recommendations come from? Is it adversarially chosen? Is it actually the wrong side that we're listening to? And as a cryptographer who has interest in making the world better, I'm very happy about the recent developments in the sense that there is now a chance to get better crypto in, and not just the crypto of the 90s, not just the crypto designed by governments that are not my own government, not that that would be any better, but that actually is maybe a good moment now to say what one could change. So just before the Snowden stories came out, May 31st last year, Dan and I were giving a talk ranting about the NIST curves as a bad idea, also ranting about the brain pool curves as a bad idea. It's not that I'm saying any government or institution is any better there, but at that moment we got a big backlash saying, well, standards are good, standards have been chosen with the security in mind. And actually our slides from that time, I just recently went back to them, and we had on them saying, well, look, why do you use the standards? Why would you implement this? There is a little bit of what you're saying, yes, be in the same boat as everybody else. Nobody has ever been fired for using the NIST curves. That still holds, I think. I mean, if you use it, nobody can really fire you for that. But many people were giving us an answer because they're more secure. When you actually then look into the standards, what they say is, we made these choices for efficiency reasons. So not even the NIST standards say that this is for your own security, it's actually just for efficiency that these choices are there. And we have now a chance to push for better, both in terms of efficiency and in terms of security.
Okay, so I want to push back a little bit on that. I certainly agree that you should understand the properties of the boat you're in. But I don't think it's just a matter of avoiding personal blame. I think the number one thing that I was worried about post-Snowden was that we would go back to the one thing I'm not nostalgic in the 90s about, which is there was this age of snake oil, of people saying, oh, go use my cipher because this is better than those evil government-approved ciphers. And
Can I do a quick product placement?
It was, sorry?
Can I do a quick product placement? Go to snakeoil.cr.yp.to and submit your snake oil crypto. We're running a competition. It's much better than the CISA competition.
So,
we've recognized this trend.
So, there was this, time of, invent your own crypto that I'm actually really worried is going to be a legacy of Snowden, which is that we will return to this, well, I don't trust that AES stuff, my one-time pad software is good enough for me, and it'll keep those government people out there because they won't be able to read my thoughts with it. That's much more harmful than the alternative.
I think we can all agree on stick to stuff that has received a lot of public vetting. I mean, you don't want to do something which is going out on a limb. You want to do something which is lots of people have published papers about and looked at, and then you can feel some confidence in it.
Okay, this is Sam Weber. Now, I expect that at some point the video for this panel will be shown to some junior professor who's gotten her PhD on some nice, advanced, horribly complex crypto, and she's now thinking, okay, look, I'm not a UI person, I can't do usability, am I screwed? What are these people saying? So is there any advice you can give to somebody who's trained in all these advanced math as to how to select problems that are going to be useful instead of just sort of doing the present useless stuff?
Dan?
It's so tempting to put the attacker hat back on, but I'll try to resist. I've seen lots of cases where people are trained in math, for instance, and they say, oh, I'd like to get into crypto and apply what I know about math to crypto. And you can see the same thing from lots of other fields. Like people will, for instance, learn about formal verification and then jump into crypto and say, I'd like to see what I can do with formal verification in crypto. And same for lots of other fields. Languages, what can I do with languages in crypto? And the results are quite mixed. Sometimes it's successful, and sometimes it ends up being a complete disaster. I think if people are saying, okay, I want to take what I know and apply it to some other field, then they're often missing the evaluation of, okay, is that actually the right thing to do? And sometimes it works out well. So there are lots of success cases of people who went from, for instance, math into crypto and have produced some great stuff. But there's also lots of warning cases where I wouldn't say that the pattern of somebody starting from something else and they say, okay, I would like to apply that something else, if I'm understanding the pattern that you're talking about, if they say, I want to apply this to crypto, then I'm worried that can get them into trouble because I've seen lots of cases of that happen.
I actually think you're thinking of cryptographers who are theory cryptographers and will become more practical.
Yeah, that's the direction.
So I think there is a huge space where more theory could look at practical things. It's just the question of, well, you don't get to design the new exciting scheme as something, but where we would really welcome some more eyes is on existing crypto. And okay, there was, for instance, at Crypto just a few days ago, a talk on like security of TLS. So taking an existing protocol, analyzing, is it secure, going for the 69 different possibilities of combining things. My preference would be going for the maybe 10 or 12 that we actually see out in the wild and looking at those and checking whether they're secure or not, but I don't mind people expanding this to like all combinations. But rather, so my advice would be look at systems that are out there that are being used or that are being proposed and check whether they're secure or formalize whether they're secure, depending on what area. Dan mentioned formal methods. That's something which is coming into crypto more and more. That's certainly has huge range of applications. But also theoretical crypto, we see several people coming from the more theory-oriented areas and now publishing at USENIX and crypto, so that's not a big problem, but you don't get to design the shiny new systems.
Yeah, the other thing is, I would advise that theory-oriented, assistant professor to, after loading up on shrimp in Santa Barbara at the crypto conference, grab a beer at the rump session, get a good night's sleep, and drive down to USENIX and make
just
friends.
Just don't schedule it at the same time ever again.
Yeah, and make friends with a bunch of systems people. I've had great collaborations with more theoretically oriented people on practical problems, and when I look at the great work that I seek to encourage more of, it's usually the result of a collaboration between somebody who's got real systems expertise and somebody who's got some real deep fundamental understanding. And that's a really powerful combination if you can learn to speak the language of the other. And that goes for us as well. Make friends with a cryptographer. They're really nice people, and actually they throw a good party in Santa Barbara every year.
It's okay for cryptographers to ask questions too? Or
I'm sorry, say again?
is it okay for cryptographers to ask questions? So Daniele
They're
Micciancio.
great people, he just said.
Yeah. So I've been listening to the questions being asked and the answer being given, and many times I was not quite sure if the answers were answering the questions. Maybe it's because of my misunderstanding of both the questions and the answers. Something that I think I heard a number of times is people asking, how can we get some guidance about how to use cryptography properly, the right way to do something interesting? And typically this is something that has nothing to do with the underlying mathematics or the security parameter or which elliptic curves is being used. It's something that you can take the basic blocks, encryption, hash functions, and so on, and use them in many innovative ways. And so the question is, do we really want to keep telling people, no, you shouldn't do it? This is our job. You use crypto for what we want you to do, or you can go ahead and try to come up with some new nice applications. Is there a way to present crypto in a way that we can enable people to do that? To me, it seems that that's what people want to do outside of cryptography. They don't want to, and of course, this something may require interaction and help from us. But I would be more than happy to help people doing that. And I feel that the theoretical cryptography that you have been always hitting on and criticizing maybe is what could give a hand here. The Knuckle, the salt library that you have been mentioning, which is something simple, minimal interface, key generation, encrypt, decrypt. Well, that's how I studied cryptography, taught by theoretical cryptographers. Then when it gets implemented, they throw all these knobs in it. And you've been complaining about the knobs. Okay, now, who wrote that library? It was not the theoretical cryptographers. It was not people like you. And you asked yourself, where do people get trained to write cryptographic software? Do they get trained at all? And I think there is a need to, maybe if not the math underlying cryptography, there is some kind of security engineering that we should really think about as something that people outside of cryptography can learn and to do new things, and not just what we have done, we have written a library for, what has been standardized, because you standardize something only after people do it. And people want to do new things. So you cannot wait for standards before people get to use the cryptography. So I wanted to ask if you have anything to say about that. Is there any hope? I don't know myself because I'm a theoretician, but as a theoretician, I'm hopeful. My time scale is in the next 100 or 200 years. Okay, I think it will happen at some point.
So this was a long question. I'm sure I'm not going to answer the right thing, but I'm sure that I did before. So a few things. I'm very, very happy to explain crypto to anybody. I'm happy to explain crypto engineering to something. I'm a professor. I like to talk about science. But I'm also happy to just present an easy one-knob solution. So the salt library is actually the one which has the one-knob solution and not many options. I'm not sure that was clear before. Mm-hmm. So I hope that having an easy option and being fully able to explain everything in there, and if anybody wants to understand what's in there, we can do that. I'm happy to put it. I have videos online explaining the math behind it, if anybody cares. But it's actually usable without understanding what all the pieces are. Just push the button. It does the authenticated encryption for you.
I think it's important to appreciate how dire the current situation is. It's not as if we're starting from some crypto that we're not quite sure about and we're trying to make it better. We're starting from 99% of the data going over the web is not encrypted and not authenticated. The competition is not HTTPS, the competition is HTTP, and similarly for every other protocol out there. We're starting from a completely disastrous situation as regards protecting user data with cryptography. Every situation where we say, yeah, you care about the authenticity of that data, maybe you care about the confidentiality of it, we should just be encrypting and authenticating all that data automatically, and that is not happening. Now, there's a real tension between saying, okay, let's get the basics done, and saying, well, we want to have some general purpose solution. If you want a general purpose solution, you know where to find OpenSSL, and that'll do all sorts of crypto stuff, and you can plug it together in all sorts of ways. But I think that's compromising actually solving the problem. I might draw an analogy to if you train a whole lot of people, this is outside crypto, if you train a whole lot of people to write kernel code, they're going to go write kernel code. And they'll think that they're doing good stuff, and they are doing good stuff, and it's useful, and then suddenly you have a kernel which is way more lines of code than you can possibly read through, and it will never be secure. Now, is that what we want to do? Well, the flexibility is worth something, and of course it's producing cool features, but how about we get some basic security done first, and then think about the fancy stuff? And if there's a conflict between having a general flexible solution and getting the basic security job done, I'll choose getting the basic security job done.
Yeah, I actually, you know, am very sympathetic to, you know, somebody doing theoretical crypto who wants to understand how to get it, you know, get crypto implemented. But I get really nervous when I hear the phrase, you know, novel applications of crypto, because we've got a lot of work to do with the boring applications of crypto before we need to prioritize the novel ones.
Please.
For the specific case of the US government FIPS standard, it's very easy to sort of buy into the hive mind and make lots and lots of snarky comments about it, right? Yes, yes.
Yeah. And let's start with the easy problems first.
Yes, yes. So I'm but a simple security engineer and spend large chunks of my life talking with very minimally technical InfoSec people. Could you pick your favorite misfeature of FIPS and how it makes the world worse? And please proceed to rant with all of the cut off, truncated words you like.
Okay.
Smart facts, maybe?
Yeah.
Yeah.
So, anecdotal, kind of also linking to what you said before, there are actually governments who help their citizens in getting crypto working. In this case, I'm thinking about the Taiwanese government, and it's very much not like what you think like Chinese government. They actually did a very nice solution. They handed out smart cards to everybody. The RSA keys were generated on the smart cards, so the government didn't actually know their secrets. And the government even got a group of people to implement plugins for Outlook to have encryption. So it was meant to be citizen-to-citizen communication, citizen-to-citizen commerce, and things like that. And they got it working back in 2003. So that's actually pretty cool. Now, the reason that I know about this is A, that we've been visiting friends in Taiwan a few times, and they told us, oh yeah, well, I can file my taxes online. Yes, I can register my grants online. It's nice, I have a smart card, you just put it in the reader and does all those things. But also, after Nadia et al.'s paper about the P's and Q's, friends of us were starting to download all these certificates. Now, the certificates, since it's a public key system, it's totally okay to have these keys public. And also they have to be public because otherwise I couldn't send to my fellow citizens somewhere in Taiwan an email. In looking through those keys, those are RSA keys, most of them were 1024-bit RSA keys. Well, we noticed some strange behavior, which then led us to look closer into these and identify that several of those smart cards were weak. Now then we needed our Taiwanese friends to really go through all the advertising text, and the advertising text was like, wow, this is really cool smart cards. There are, now it comes FIPS 130, FIPS 140-2 certified, and also BSI common criteria, so they got all the good things. Now, there was something strange that out of more than 1 million keys that we looked at, we only found like 100. That's a little too few. I mean, it was few, closer to 200, but it was too few for something which affects all smart cards. It was too many for security. I mean, it should have been 0, but it was certainly not the case that it was all of them. Now, digging into it deeper, it turned out that the Taiwanese government had changed the deal, had changed the company, and that the company that actually had to deal with from 2003 till 2007 was making some decent smart cards, at least not that we could show anything different. And then the next vendor, who started in 2007, had a batch of bad smart cards which were giving these keys. But also for the second vendor, we then were digging out the documentation, and also the second vendor got all the necessary standardization requirements and so on. Problems with standards that we encountered there were, okay, once it says standardized and verified that the standard is adhered to, people switch off their brains. For instance, in this case, the smart card has two modes. One is a FIPS mode, one is a non-FIPS mode. One should think that if you want to use the FIPS certified in your advertising text, that you would also use the FIPS mode in your products. However, it is not a given. So the FIPS the FIPS certification doesn't actually enforce that only the FIPS mode can be used. So it doesn't even achieve what is done there. Plus, in this case, they managed to certify a smart card that didn't adhere to it. Now, looking through the reports, yes, there were some mentions about maybe some irregularities, but both the testing lab in the US and the testing lab in Germany missed how bad this could work out. Most likely at the end of the frequency, but it just means people switch off their brains as soon as there's standard on it. The other example I'm thinking of is OpenSSL having implemented the dual EC because, well, somebody told them if you want to get certified, you have to implement all the random number generators, and so they implemented the one with the backdoor as well. It didn't work, as we saw in the talk today, but it still was implemented. Now they wanted to remove this bad one, and now there's even a NIST recommendation to remove it. However, removing it would mean they would lose the certification. So in that, it's another case where certification actually makes security worse. There are also examples where security is better. I mean, I've been working with testing labs, and I'm happy about every weak smart card they find and identify as weak. It's important that smart cards and crypto implementation such gets lots of eyes to look at, and in particular for smart cards, you need to have quite some equipment, so I understand the need to have an evaluation lab there because it actually costs money to do it, but just having the certification does not actually prove that much. Couldn't possibly have covered everything. There's so much more.
Wait, does anybody actually like FIPS, the whole certification stuff?
I like hearing about specific critiques of it.
Any other examples?
Well, I mean, not to hammer on dual EC, I mean, we had a great paper on practical, exploits on dual EC at the conference, but, let's not point the finger too exclusively at NIST and NSA here. This, serious doubts about this were raised in 2007 at the Crypto Rump session, and everybody just kind of yawned.
No.
Right. Well, the community, didn't demand that it get removed. We, as a community, fell down on the job as a whole. You don't think so?
So I agree that I was not aware it was used, so yes, failure on me. However, you can't say that the community just yawned, because, I mean, I was at the RAM session, we have videos from the RAM session, there was quite a bit of excitement in the room about this.
Yeah,
also,
sure. I mean, all the cryptographers were very excited about it, but and it was still in the standard years later. And then we got re-surprised by it in 2013.
And Schneier's article in Wired got quite some attention. I'm very glad to the people at EFF and the representative whose name escapes me, but somebody working together with Matt Green for actually FOIAing the documents from NIST, which now show us a bit more about how this whole process happened and what was going on there. And it now showed us that, yeah, the Wired article actually did get noticed and did get quite some attention in NIST, and they saw the need to react to it. However, what these documents show is that within NIST, they consulted with their partner NSA, whom they considered as the knowledgeable partner in these matters, and wrote a well-worded response to Schneier saying, yes, we have considered this internally, and we think it's all fine. I mean, this document is now online, and looking at this, it's just, to me, it's more, it was the wrong attitude towards agencies that was the problem. they believe that if they say we looked into this and it's good, that people believed we looked into this and it's good. I mean, they certainly looked into this.
Yeah, and, you know, I think shame on us for that.
I think a lot of what makes it difficult to see all the problems coming up is that the whole ecosystem of cryptographic standards and implementations out there is so complicated. Looking at the standard side, NIST, they have some well-known things like the AS competition, the SHA-3 competition, but at the same time, I was about to use a bad word, I'm sorry. They are releasing one standard after another, and then recommendations and guidelines and all sorts of stuff where each of these things is 100 pages or more, and there's just way too much to review. It was purely by accident that, for example, EAX prime, which is a variant of EAX. EAX is a very reasonable way to do authenticated encryption. EAX prime is a proposal to make it more efficient. Now, this is like the moment in the movie where you see, you know, the dagger sticking out of the house, and you can tell somebody in the fight scene is going to get impaled on the dagger. Okay, we're going to make EAX more efficient by tweaking it like this. And sure enough, EAX prime was broken, and it was just barely broken in time for NIST to not standardize it. But who knows how many more problems there are in standards. The AES GCM standard that tons and tons of people are using, that has a bug in the security proof, and it wasn't discovered until years after NIST issued the standard. Now, it's not that it's seriously broken, as far as we know, but there's just so much stuff out there that it's really tough to review. There's
It's a denial of service attack.
Yeah, there's a few things out there that the community has actually reviewed and is confident in. And it's a really small subset of the things that are standardized. And then if people say, oh, well, it's standard and you can get certification for it, that does not mean that anybody's actually reviewed it.
I'm sure the definition of a standard second is pretty good. You know, NIST maintains that.
The meter. The meter, but only for metric countries.
Yeah.
So how do we get the bad stuff removed from the standard?
Propose good stuff. And show that the bad stuff is broken. I mean, that's why I said before, it's better the situation now than a year and a half ago in that more people are looking at the standards with skepticism. More American people are looking at the standards with skepticism. I notice a big difference between what Europeans were thinking about the NIST standards, where I'm excluding the UK from Europe, and what colleagues from America were thinking about the NIST standards. It's a very different attitude that we in Europe, so I've worked in Germany, the Netherlands, Denmark, I have enough colleagues in France that we talk about, and there's always this feeling, oh yeah, well, the NSA standards or the NIST standards, we don't know where they come from, and we have this feeling that they might be adversarial. It's something which I very rarely could match with what my, well, okay, excluding Dan here, among my American friends, but lots of people here seem to have believed that the NIST standards are coming from the good side. And just knowing that that's not necessarily a given already helps.
Okay, I want to take a quick straw poll here in answer to that question, because we have a uniquely talented person on the stage, right, who knows about crypto stuff and also knows how to build really, really conservative, good software.
I'm going to hide under the table now.
So should Dan spend the next N months of his life, how many, you get to vote. So one thing you're going to vote on, should Dan spend the next N months of his life picking a NIST standard and picking it apart, or giving me a secure email system I can use? How many people would like him to spend his time picking apart a NIST standard as his next project? Okay, how many people want secure email? Okay, thank you.
Secure email wins for those of you who are listening but not watching. No, I think, you know, he's going to do one. He's going to do something. Dan's going to be Dan, right? Yeah.
But I mean, in
You
the old
fold under
system,
peer
nobody
pressure?
would have used Dan's new email system because it's not standards compliant.
So I have to, coming from the practical side of cryptography, I was forced to actually defend the theoretical cryptographers. So thank you very much for allowing me to play the devil's advocate now for this discussion. I'm from the FSC community. I'm not from the theoretical cryptography. So
FSE is symmetric crypto.
and doing cryptanalysis, so real stuff, sort of. In any case, parts of the complaints about the theoretical community, even though I share most of the criticism, is somewhat related to the gap that we have between cryptography and computer security. For example, when it comes to the SHA-3 competition, one of the problems theoreticians had to face was the fact that people take hash functions, which is a design that cryptographers had with this idea that it's going to be used for one thing, and use them to do everything. Everything was based on with hash functions. Everybody were using hash functions in very imaginative ways. And then when the SHA-3 competition went out, you had to deal with security requirements, which made no sense from cryptographic point of view, because if you want to use key derivation functions instead of using HMAC, we have the theoretical constructions to deal with that. You don't need to go through hash functions which were designed to be unkeyed primitives. So by the fact that the practical community forced the crypto community to start working with hash functions which do things which are not the way it was designed. Hash functions were never designed to be keyed, though theoreticians disagree. They think that hash functions should be keyed, but in practice, hash functions are not keyed. And then the computer security community uses it in a new imaginative way, and then we have to cover up the security crisis that comes out. And again, speaking on behalf of the theoreticians, that I don't see any of them defending themselves here. I wonder why. They had issues with modeling this. And then we come as the practitioners to try and implement new hash functions, design new hash functions. On one hand, we have the theoreticians that ask for weird, theoretical, indistinguishable, pseudo-random oracle. Okay, you just have here a list of weird titles. And then on the other hand, we need also to satisfy what the computer security community wants, which was very different. So we had this gap, and I think that in the case of SHA-3, it somehow went okay at the end. But in other cases, when the community, the computer security community wants something which is complicated, like people ask here for solutions, for general solutions, the theoretical cryptographers sometimes try to do that. But the thing is that once there is a solution, it's automatically being used to other things, and then we are forced in the standard problem that computer security has. You implement something for one environment, then it's going to be used in another environment, and then everybody are worried because, hey, it was broken, but it was broken because we misused it. So just defending a bit the theoretical people, I'm terribly sorry for that. And they do have some solutions for the more complicated stuff that people asked about. You just have to dig into the papers, disregard the fact that it says random oracle, or common reference string, or any of these buzzwords that leakage resilient, non-malleable, zero knowledge, resettable, whatever. So this was my comment, not really a question, but I can hear your
Respond?
I'll tell a maybe tangentially relevant story. In the Netherlands, there's an intrusion detection system. Well, of course, there's lots of intrusion detection systems. You can install these things on their network, but no, this one's better because it's distributed and run by the government of the Netherlands. Now, they have their central machines, they have their boxes that they install on your network and everybody else's network, which are, of course, doing exactly what they tell you that the boxes are doing, namely looking for intrusions. Now, how do they define intrusions? Well, currently, they say they can only upgrade the boxes by coming physically to upgrade them. Maybe that's true. Currently, the configuration that they can do remotely of the boxes, they say, is they can tell the boxes, please watch for anybody who's contacting the following botnet command and control server, where they dynamically specify what that is. For instance, tell me the IP address of anybody on your network who's looking up, there's a botnet command and control server called aljazeera.net. That's a news site for anybody who doesn't recognize the name. But it's a bad news site because it starts with al. Now, within half an hour, the sysadmin is allowed to watch the data and stop it from going back to the government-operated system. And they have this, that's really good protection for your privacy. And they have the following anonymization. They take your IP address and they hash it.
With a salt.
There is a salt, yeah. So that would make the theoreticians happy, the fact that there's a salt. Draw your own conclusions.
I think I have an actual question. Because I've been listening to you guys and trying to make some sense of of the space. And there's this idea that so on the one hand, standards are tremendously harmful because, you know, we don't know what they're cooking into them, and they keep the people from implementing actually good things. On the other hand, the concept of standardization is exactly what you want, because you've been talking about this idea that you know, there are these good things in the salt library, for example. We learn the right way to do it, we should do it that way, and everyone should do it that way. So the question is, in the absence of how do we get to standardization
Without standards.
Without standards and without standards bodies and so on, and how do we make the right things the standards as a community? Is there any way to do that? Is that a sort of a world peace complete problem, as we mentioned? So, you know.
WP complete.
So first of all, yes, I agree, we need some sort of standards. I mean, if you look at the TLS protocol, you don't want to have, like, everybody use its own ciphers and then you can't talk to one another. It's just a question, like, who makes the standards, how many eyes are on this, and how international is it? So I'm very happy, for instance, at the moment with the IETF, they have a cryptography working group, they just changed leadership. It used to be co-led by Cisco and NSA. The NSA guy is still there, but will disappear at the end of the year. And there is now one researcher from industry, one from academia, leading it together, trying to get more people involved, and suddenly there's lots of discussions on the mailing lists. I have the feeling that that is going in the right direction, to have more involvement by people who actually do things, and they're trying to reach out to the research community, trying to reach out to the industry community. So.
Yeah, I mean, I think that it's worth distinguishing, you know, the standards process that, you know, when it gets to be a certain size, carries with it a certain amount of baggage, which is you know, one problem, and the second problem of, right now, we're kind of mistrustful of the federal government, and in particular NIST, which is you know, which is another problem, but it's kind of separable from that first one. You know, one of the things that's nice about the IETF is its standards process tries at least to be fairly lightweight given its scale, and you know, that's the scale of the IETF has gone up, and so it's no longer as lightweight as it was back in the good old days, but it still is aiming for that sort of lightweightness.
And transparent. I think that's the important thing.
That's right. Yeah. So, you know, standards processes modeled on that as opposed to the ITU, you know, are good.
I think maybe what I'd suggest as a way to see what's good is, I know it's not an easy thing to do, but read the papers. I mean, there's papers from the 90s by respected cryptanalysts saying don't use MD5. And somehow that memo was totally clear from the papers and didn't get to the practitioners for, well, something like 10 years. And that's a real problem. And I think you can solve this problem by actually reading what the cryptanalysts are saying. I mean, they're doing tons of work to say, for the systems that they're looking at, these are good, these are bad. And it's not always condensed into a nice, simple form, but I honestly find that with the work of going through the papers, it's more informative than trying to get the same kind of information out of a standards process. There's so many pressures on a standardization body which have nothing to do with security, whereas the people who are doing cryptanalysis, their sole focus is the security. So I would put in a vote for read the papers.
Listen to OR.
And that goes back to something else you said very early, which is the cross-pollination. Get the cryptographers to using security and get the using security people to crypto.
Speaking as the person who added secrets to hashes in 1990 for the cryptographic handshake authentication protocol and took no end of word on the bottom of the screen from the cryptographic community, in fact was required to take the word cryptographic out of the name of the protocol and change it to challenge. Of course, in that case, it would be challenge response authentication protocol, which they didn't like the acronym. But adding a secret properly to a hash and to a one-way function, and you think of it as a one-way function, as an expression function, is perfectly reasonable. And I think we went on to show that it was perfectly reasonable. as long as you had an iteration and compression within the function and counted how many bits you're feeding into it and designed it properly. That people went on. I had another thing called IPMac, which very carefully did that. And that in between, or slightly afterwards, somebody came up with something called HMac, which didn't. This is not the fault, but I ended up putting at the bottom of every one of my security papers after that, this was designed by network protocol engineers with an interest in cryptography, not by cryptographers with an interest in network protocols. Okay? Again, and on MD5, you are absolutely wrong. We do read the papers. And one of the, like, halfway into the second page, it very clearly says the analysis for MD5 is broken only when there is not a random secret involved. And since we were using it with a random secret involved, then the analysis didn't apply, which is why we ignored the advice. And those protocols are still good today using MD5. So sometimes we get cryptographic purists, and maybe you want to speak about that, who look down upon the hoi polloi who aren't, are merely using these to create security protocols, that it is not perfect or perfect in their minds or whatever. We're merely trying to get something that is good done.
Yeah, I don't think it's a question of where the protocol is coming from, whether it's labeled as being a protocol from a cryptographer or a protocol from a network protocol engineer. It's a question of, has the protocol been well designed? Has it survived review? And that's something that we can figure out from watching the public record. So I think that I'm very much in agreement that, yeah, there's lots of great stuff. I would say more great stuff has come from the practical community trying to get jobs done than from the theoretical or purist or whatever cryptographic community. Because the people getting jobs done actually know what the security problems are that they're trying to solve. And, well, of course there's lots of mistakes, but there's lots of times when people will just do the job right. And then those things we really have to focus on and make sure that we're absolutely sure about those, and then just get everybody using them and stop doing random variations of them.
So
naming issue. I mean, I think what always bringing up is that a hash function per se doesn't have a key. Now, then you can call it a keyed hash function or something, but you could have also called it something totally different and avoided the confusion, and also then have said, okay, well, this thing based on MD5 is still secure, while the use of MD5 as a hash function is not secure. And
well, we did give it different names. We love to name things, do things. I like to name CHAP, we named it IPMac, we had LMAC, HMac, KPMac, I can't remember, we had all kinds of Macs.
And it's good that you personally read the papers and noticed that your scheme is fine. However, for instance, when you look at the Microsoft code signing, which was used in the Gauss attack, they also maybe read the paper and didn't get till page 5 or didn't understand the consequences, and they just use MD5 as an unkeyed compression function and use it in signing where it's just really not suitable. So this was, I don't think, a comment towards you. It was a comment towards, well, we saw lots of users of MD5. We have seen some users of MD5 being weaponized later on, which is apparently possible because somebody didn't read the papers.
But I'm just saying, from the beginning, we got nothing but crap from the theoretical cryptographers.
All right, give us the names of the culprits.
Yeah.
Them.
Yeah.
Not you.
Yeah. Yeah.
Not any one of you.
Right.
And the one in the middle was actually quite helpful.
Okay, so I apologize for that, but yeah, I was actually on a panel recently where my favorite question from the audience was, why are cryptographers so unpleasant? So I hope we've helped answer that.
So I'm sorry to say, but we're actually out of time, so I'd like to ask each of you if you have any closing statement you'd like to make.
I apologize for being a cryptographer and unpleasant to deal with.
I look forward to using Dan's email encryption system.
Okay, seriously, I think just keep it simple, stupid, and then it's, I mean, I'm not trying to call anybody stupid. Oh shit. Oh.
holding it for an hour and a half.
Let us please thank our panel.